this video, we're going to start talking about how we can work with the rational operations when we're doing division of two rational expressions. In particular, we're going to pay more attention to the domain changes as we go through the process. So as we look at the division and the original domain restriction for any type of problem, there are really a few things we want to look at. So if we look at part A as an example, we have really two rational expressions to start with, and individually we don't want the denominators to be 0 to start with for our expression over here. So we first don't want either the 3x squared minus 12x to be equal to 0, and we also don't want 3x squared plus 6x to be equal to 0 over here. But in addition, when we're doing division, we always want to make sure what we are dividing by is also not equal to 0. So entirely, we're saying this whole thing cannot be equal to 0. Otherwise, we would be dividing a rational expression by 0. That's going to be undefined. And because of this, we want to make sure this whole expression doesn't equal to 0. And when that entire expression is equal to 0, that only happens when our numerator is 0, because 0 divided by whatever denominator is going to be equal to 0. As long as we made sure that denominator of 3x squared plus 6 is not equal to 0, this rational expression is defined. And therefore, if we want to make sure the entire expression is non-zero, we also want to check that 5x squared plus 20x is also not equal to 0 over here. And there are really three parts we have to be concerned about in this entire process. So let's work at them one at a time. For the first part, we can start with GCF. The greatest common factor here will be 3x. We can factor out, leaving us with x minus 4 doesn't equal to 0. Therefore, x doesn't equal to 0, and x doesn't equal to 4. For the second part, 3x squared plus 6x, we can use GCF of 3x again, leaving us with x plus 2 doesn't equal to 0. So again, x doesn't equal to 0, and x doesn't equal to negative 2. Lastly, we can have a GCF of 5x times x plus 4 doesn't equal to 0. So x doesn't equal to 0, and x doesn't equal to negative 4. So now, in order to list the domain restriction of the initial operation, we want to make sure that we would want to work with the domain such that we have x doesn't equal to 0, x doesn't equal to negative 2. I'm actually just going to list them out as individual numbers. Negative 2, negative 4, and I left the 4 out over here. So x cannot be any of these values. In this case, that's our original domain that we have to be concerned about. So this is something new that we have to include in our domain restriction when we're dividing certain things. And when we're going through the operation, we can think about that division of a fraction can be turned into a multiplication by its reciprocal. So as we do this, we can kind of flip the second expression over here. I'm going to just copy down the first rational expression first, and we can turn this to be a multiplication of 3x squared plus 6x all over 5x squared plus 20x. And at this moment, I think you can see why we really want to make sure that 5x squared plus 20x is non-zero to start with, because now this becomes our new denominator. So that is a domain restriction that we have to worry about, and that gave us x doesn't equal to 0 and x doesn't equal to negative 4. Now from here, we can start working with a factoring process. X squared minus 16 is a difference of squares, so that's x plus 4, x minus 4. That can be factored out. Everything else we actually already factored when we were looking for the domain restriction. We get 3x times x minus 4 in the denominator, and then here we have 3x times x plus 2 over 5x times x plus 4. So I'm just referring to what I did in the left column for the factorization process. It's all GCF factoring. And then we can go ahead and start canceling things out over here. And here we have x plus 4 canceled out. We use the fact that x doesn't equal to negative 4, which was in our original domain restriction. And we also have x minus 4, so we need to make sure x doesn't equal to positive 4, which we also made sure in the original domain restriction. 3x can cancel each other out. By doing this cancellation, we require x doesn't equal to 0. And that's it. Nothing else can be canceled out anymore. We're left with x plus 2 all over 5x. So we can see in the final result, we are left with 5x alone in the denominator. So the domain restriction of the final part is just going to be x such that x doesn't equal to 0 over here. So we can say the starting expression and the ending expressions are equal except for when x is equal to negative 4, 4, and negative 2 over here. And that's how the domain entirely changed if you compare the starting domain restriction with the ending domain restriction over here. The difference is negative 2, negative 4, and positive 4. Now moving on to part B, we have a rational expression divided by p plus 1 squared. And for the second expression, we don't have a denominator right away, so we don't have to worry about the domain restriction for the denominator. But we also want to check the same criteria. We want to make sure any existing denominator is not equal to 0, so p cubed cannot be equal to 0. Also, what we're dividing by cannot be 0, so p plus 1 squared cannot be 0. These are the restrictions we have to consider. And now if we p cubed, it doesn't equal to 0. The only way that cube can be 0 is p doesn't equal to 0. And then for the second criteria, we need to use a square root property. That gives us p plus 1 doesn't equal to 0, or p doesn't equal to negative 1. So the original domain will be p such that p doesn't equal to 0, and p doesn't equal to negative 1. Now let's look at this operation. So I'm going to keep the first expression, and that division can be turned into a multiplication by reciprocal. Remember, we can always turn any expression to be over 1, and that makes it a little easier to track what's the numerator and what's the denominator for our purpose. Now moving on, if we want to simplify, we can go ahead and factor the numerator, which turns out to be p minus 8 and p plus 1 all over p cubed times 1 over p plus 1 squared. And with this, we can go ahead and cancel out p plus 1 as a common factor. And as we cancel this out, we are relying on the fact that p doesn't equal to negative 1. And here, if we simplify the result, we get p minus 8 over p cubed times p plus 1 over here. Now if we look at the final domain, we still have p cubed times p plus 1, which is exactly what we started with a domain restriction. So these are still the factors we need to consider. So we still get p such that p doesn't equal to 0 and p doesn't equal to negative 1 as a result. So we can see the domain did not change. Moving on to part C, we still want to go through the same strategy. So the first restriction I have is x squared minus 6x minus 16 is not equal to 0. Then I also want to make sure the other denominator is non-zero. But moreover, I want to make sure this entire expression that I'm dividing by is not equal to 0. So I want to make sure x squared minus x minus 12 doesn't equal to 0. So these are the restrictions, and we can start solving from here. And this is a good factoring process. Feel free to pause the video if you want more time to factor it properly, and I encourage you to do this yourself, because factoring is really this process that you'll get fast really quickly as you practice more, but with a lack of practice it could be daunting when you see one. And now looking back to the first expression, we can factor to be x minus 2, x minus 8, x plus 2 doesn't equal to 0, therefore x doesn't equal to 8, and x doesn't equal to negative 2. Then we have the second expression that can be factored out as x minus 8, x plus 3 doesn't equal to 0, and therefore x doesn't equal to 8 again, and also we have x doesn't equal to negative 3. And lastly, for the last expression, we have x minus 4 times x plus 3 as a factored form. That doesn't equal to 0, and x doesn't equal to 4, and x doesn't equal to negative 3. So if we want to combine all the restrictions together, we can put together the domain. It's x such that x doesn't equal to 8, negative 2, negative 3, and 4 over here. So in this case, these are the restrictions we start with, and we can see when we start completing the operation what ends up happening in the process and at the end. So we can see a lot of the numerator and denominator have been in factored form already, just as we're solving the domain restriction. So I'm going to go ahead and factor the first numerator. Might as well do this right now. And here we can get the factoring of x minus 4 times x minus 8. In this case, that would satisfy the condition. And for the first denominator, we factored it as x minus 8 times x plus 2. You can refer to the left. And I can turn this division into multiplication. And then now my denominator is going to be the original numerator. So the original numerator was factored as x minus 4 times x plus 3, and then we're flipping the denominator up, which gives us x minus 8 times x plus 3. So make sure you pay attention to this change of operation over here. That's why our numerator and denominator switched in this case. And once you have this form, everything's fully factored, we can start canceling out common factors. X minus 8 right away cancel each other out. X plus 3 again cancel each other out. And as you're doing the cancellation, you can kind of see why we have so many repeated restrictions as we were solving it earlier on the left column as well. So even though we had two restrictions from each inequality, we end up only with 4 numbers. That's why we have all the cancellation within the same rational expression already. That's why a lot of times they're repeated. Just like here, we have x doesn't equal to 8, x doesn't equal to 8 again, and similarly x doesn't equal to negative 3 repeated itself. And then in addition, we also have this cancellation of x minus 4 doesn't equal to 0 that's required for x to be not equal to 4. So altogether, with the cancellation we have incorporated, we needed to make sure x doesn't equal to 4, so we can cancel out x minus 4, x doesn't equal to 8, so we can cancel out x minus 8, and x doesn't equal to negative 3, so we can cancel out x plus 3. And altogether, we would have x minus 8 over x plus 2 that's left. And in the final answer, we will see the domain, the new domain we are left with is x such that x doesn't equal to negative 2. So we can see the changed values are really happening as what we listed out over here. Or if you compare the domain restrictions, we had 8, negative 3, and 4 being taken care of, or essentially it's not the domain restriction in the final result anymore, but you can still see it was being incorporated in the whole operation over here. Now lastly to part D. If we want to simplify that, same thing as before. And in this problem you can see we have some AC method factoring coming up over here. So first we want to make sure 5x squared plus 6x plus 1 doesn't equal to 0. I'm going to leave a bit more room because it's an AC method. And then I want to make sure the second denominator, x squared plus 2x plus 1, doesn't equal to 0. And also the second numerator doesn't equal to 0 because I want to make sure I'm not dividing by 0. So I get x squared minus 5x plus 4 doesn't equal to 0. So let's start from the top. I have an AC method problem. I want the product to be equal to a times c, which is 5. So I want product equal to 5 times 1. It's 5. And I want the sum to be equal to 6. And it works out pretty nicely. We get just 5 and 1 as the two numbers. So I can really rewrite this to be 5x squared plus 5x plus 1x plus 1 doesn't equal to 0. And group them together, first two, last two, connected by addition. Then the first group, we have 5x in common. That leaves us x plus 1, plus second group just remains the same as x plus 1. That doesn't equal to 0, so x plus 1 is a common factor, leaving us with 5x plus 1 doesn't equal to 0. So if we solve it, x doesn't equal to negative 1, and x doesn't equal to negative 1/5 over here. And to save space, I skipped a little bit of the steps for solving linear equations, but definitely feel free to write out as many steps as you need to complete the work. For the second restriction, again, if you don't recognize this as a perfect square, you can still get the same result by just finding two numbers that multiply out to be 1, add up to be 2. Turns out they're both 1s. And if you recognize it, it's a perfect square trinomial. We just have x plus 1 squared doesn't equal to 0. And you can use a square root property to get x plus 1 doesn't equal to 0, therefore x doesn't equal to negative 1. Again, we see that there are some repeated values that ends up showing up in the domain restriction. Lastly, we have this factoring that can be done into x minus 4 times x minus 1 doesn't equal to 0. And therefore x doesn't equal to 4 and x doesn't equal to positive 1. So altogether, the domain restriction is x such that x doesn't equal to negative 1, negative 1/5, and 4, 1 over here. So that's the original domain restriction. Now moving on to actually completing the operation. You can see the domain restriction almost takes longer than the actual operation, because that's where a lot of the factoring process happens. First, I'm going to just go ahead and factor the 5x squared minus 4x minus 1 right away. I'm going to write this as its own thing. If I want to factor that, I need to use AC method, meaning I want the product to be a times c, which is negative 5. I want the sum to be negative 4. Let me write this a little bit better. So I want product to be negative 5 and sum to be negative 4. Alright, and the two numbers we should have in this case is going to be negative 5 and positive 1. And with this information, we can rewrite the expression to be 5x squared minus 5x plus 1x minus 1. So now we can put things into groups. So these are groups connected by addition. So for the first group, we have 5x in common, leaving x minus 1, plus the second is just x minus 1. They don't share any GCF, so we won't factor it. And that leaves us with 5x plus 1 times x minus 1. Don't forget to plus 1 over here, even though we don't have anything left. We need that multiplied by 1. And as a result, we can say this original operation, we can go back to that, is really equal to 5x plus 1 times x minus 1 over, again I'm referring to the right hand side for our factoring, or factored result of each expression. And now I'm changing this to a multiplication problem again, meaning I'm going to flip the numerator and denominator in the second expression. So the numerator now should be x plus 1 squared, because that's how we factored out x squared plus 2x plus 1, and the denominator now should be x minus 4 and multiplied by x minus 1 over here. So up to this point, the domain restrictions will be the same, and we have x minus 1 cancel each other out, x plus 1 cancel each other out, 5x plus 1 canceling each other out. And in order to do these cancellation, we need x to not be negative 1/5, and x doesn't equal to positive 1, and x doesn't equal to negative 1. So these are the factors we canceled out, and we want to make sure we denote these. And once we have this result, we can see the fully simplified form becomes just x plus 1 on top and x minus 4 in the denominator. So for the last part, the domain is just x such that x doesn't equal to 4. And everything else had been incorporated one way or another in this cancellation process. And you can see the differences between the starting domain and ending domain is exactly what we noted in red over here, or what I highlighted in the domain restriction.